Empty space is not empty. Even in the quietest regions of the universe, far from stars and galaxies, where no atoms drift and no light shines, something is always happening. The vacuum of space, which once seemed like perfect nothingness, is now understood as a restless, subtle field of activity. Particles appear and vanish. Energy flickers. Reality hums softly beneath silence. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these calm explorations alive, and I hold that kindness with sincere thanks. Now, we begin with the first truth. Part 1. Is empty space truly empty? What do we mean when we say nothing? For most of human history, empty space was imagined as a void, a simple absence where matter ends and silence begins. But modern physics paints a very different picture. Even when every atom is removed, space itself remains, structured by invisible fields that never fully rest. The quantum vacuum is not an empty stage waiting for actors, but a living backdrop, quietly active, even when nothing seems to be there. And this realization changes what emptiness means forever. To understand why, it helps to begin with how deeply rooted the idea of nothingness once was. Ancient philosophers argued about whether a vacuum could exist at all. Aristotle believed nature abhorred a void, insisting that empty space was impossible. For centuries, this intuition felt correct. Air rushed to fill gaps, water flowed where space opened, emptiness seemed unstable, fleeting, almost fictional. Even as science matured, space was still treated as a passive container, a silent arena where matter moved but which itself did nothing. That view began to change in the early 20th century, when physicists started to probe the smallest scales of reality. Atoms, once thought indivisible, revealed internal structure. Electrons orbited nuclei. Energy came in discrete packets. And slowly, almost reluctantly, scientists realized that the old picture of emptiness could not survive. When they removed matter from a region of space, something remained. Not particles, not light, but fields. Subtle, mathematical objects that filled every point, whether or not anything visible was present. In classical physics, a field is a simple idea. A temperature field tells you how warm it is at every location. A gravitational field describes how mass pulls on other mass. But in quantum physics, fields are more fundamental than particles themselves. Every type of particle is associated with a field that exists everywhere, all the time. Electrons are excitations of the electron field. Photons are ripples in the electromagnetic field. Even when no ripples are present, the field does not disappear. It remains quietly stretched across the universe. This means that what we call empty space is actually space where these fields are in their lowest possible energy state. Physicists call this the vacuum state. But lowest energy does not mean zero energy. And this is where the story becomes truly strange. According to quantum mechanics, fields cannot be completely still. There is a fundamental limit to how precisely certain properties can be defined, known as the uncertainty principle. If a field's energy were exactly zero, its behavior would be perfectly fixed, and that is not allowed. So even in the deepest vacuum, far from stars and galaxies, the fields that fill space continue to fluctuate. Their energy rises and falls slightly. Their values shift and shimmer. This restless baseline is known as zero-point energy. It is not something added to space, it is built in, a quiet motion that cannot be removed, no matter how cold or empty the universe becomes. You can think of it as a kind of cosmic hum, not a sound, but a presence. Even as you sit perfectly still, even as space appears calm and dark, the vacuum is alive with microscopic activity. These fluctuations are not directly visible, but they are real. They influence how particles behave. They shift energy levels inside atoms. They subtly alter the forces between objects. One of the most remarkable consequences of this restless vacuum is the brief appearance of what physicists call virtual particles. In the quantum picture, energy and time are linked by uncertainty. Over very short times, small amounts of energy can appear and disappear without violating the laws of physics. The vacuum takes advantage of this freedom. Particle-antiparticle pairs can momentarily emerge from the background, exist for an instant, and then vanish again. These particles are not imaginary. They cannot be observed directly, but their effects can be measured with extraordinary precision. They slightly change the charge of the electron. They alter how light travels through space. They even contribute to forces that can be detected in laboratory experiments. The vacuum, once thought empty, behaves more like a sea, gently bubbling at scales far smaller than anything we can see. This realization forces a quiet shift in perspective. Emptiness is no longer the absence of reality. It is a particular state of reality, a structured, energetic condition governed by the same laws as everything else. The vacuum is not a backdrop behind physics. It is part of physics itself. Even gravity responds to this subtle activity. According to Einstein's theory of general relativity, energy tells space how to curve. If the vacuum contains energy, then empty space should still gravitate. This leads to one of the deepest puzzles in modern science. When physicists calculate the expected energy of the vacuum using quantum theory, they get an enormous number, far larger than what we observe in the expansion of the universe. Somewhere between theory and reality, something is missing. And yet, the vacuum's influence cannot be denied. Without it, atoms would not behave as they do. The structure of matter would change. Even the stability of the universe might be different. The calm emptiness between stars plays an active role in shaping what exists. As you breathe right now, you are surrounded by this invisible framework. Between every atom in your body, between every molecule of air, lies space filled with fields in their lowest energy state, not empty, not silent, simply subtle. The stillness you feel is not the absence of motion, but the balance of countless fluctuations too small to disturb your senses. This is one of the quiet triumphs of modern physics. It teaches us humility. What once seemed obvious turned out to be incomplete. What once seemed like nothing turned out to be something profound. The vacuum reminds us that nature often hides its deepest activity beneath calm surfaces. And as we begin this journey, this first truth settles gently into place. Empty space is not truly empty. It is the foundation upon which particles appear, forces act, and the universe evolves. A quiet presence, always there, always active, even when nothing seems to be happening. And as we continue forward, one question naturally follows. If the vacuum is alive with energy, how did we first discover that it refuses to stay still? Part 2. The discovery of the vacuum that wasn't quiet. How did scientists first realize that nothingness was unstable? The answer emerged not from philosophy, but from experiments that refused to behave as expected. When early quantum theorists examined atoms at their lowest possible energies, they found motion where none should exist. Even at absolute zero, particles refused to sit still. This restless behavior hinted that the vacuum itself carried energy, a baseline hum woven into the fabric of reality. At the turn of the 20th century, physics seemed nearly complete. Classical mechanics described motion with elegance. Thermodynamics explained heat and energy. And electromagnetism unified electricity, magnetism, and light. In this framework, empty space was still imagined as passive and inert. If all matter were removed and all motion cooled away, nothing should remain. Absolute zero, the lowest possible temperature, was expected to bring perfect stillness. But when physicists began to study matter at increasingly small scales, this expectation quietly unraveled. The first cracks appeared in the study of atomic spectra. When scientists heated gases and observed the light they emitted, they found precise, discrete lines rather than a smooth rainbow. Atoms released energy in specific amounts, suggesting that their internal motion was quantized. This was already strange. But what puzzled researchers even more was what happened when atoms were cooled instead of heated. As temperature dropped, the motion of atoms slowed, just as classical physics predicted. Vibrations weakened, energy levels lowered, but no matter how carefully scientists tried, they could never remove all motion. There was always a final residue, a minimum energy that could not be extracted. Even at absolute zero, atoms retained a subtle internal activity. At first, This seemed like a limitation of experimental technique. Perhaps absolute zero simply could not be reached. But as theoretical tools improved, physicists realized something deeper was at work. The residual motion was not a flaw in measurement, it was required by the laws of nature themselves. This realization crystallized with the development of quantum mechanics in the 1920s. Werner Heisenberg introduced a principle that would permanently alter our understanding of stillness. His uncertainty principle showed that certain pairs of physical properties, such as position and momentum, cannot both be precisely defined at the same time. The more exactly one is known, the less certain the other becomes. This was not a limitation of instruments, it was a fundamental rule, and it carried a profound implication. If a particle were completely still, with zero momentum, its position would be perfectly defined. That state is forbidden. Nature does not allow it. As a result, particles must always retain some motion. Even in their lowest energy state, they jitter gently, constrained but never frozen. This minimum motion is known as zero-point motion, and the energy associated with it is zero-point energy. Once this idea was accepted for particles, physicists began to apply it to fields. In quantum theory, fields are the most basic entities. They exist everywhere, even where no particles are present. If particles cannot be perfectly still, then fields cannot be perfectly quiet either. This was a radical shift. It meant that empty space itself, defined as a region without particles, still contained fluctuating fields. The vacuum was not a blank canvas, it was a dynamic system in its own right. One of the earliest and clearest signs of this came from the study of harmonic oscillators, simple systems that describe everything from vibrating springs to electromagnetic fields. In classical physics, a harmonic oscillator at rest has zero energy. But when physicists applied quantum rules, they found that even the ground state carried energy. The oscillator could not stop moving entirely. This mathematical result seemed abstract at first, but its consequences were real. When applied to the electromagnetic field, it implied that even in complete darkness, with no photons present, the field still fluctuated. These fluctuations were tiny, but they were everywhere. As experimental precision improved, the vacuum began to reveal itself more clearly. One key moment came with the study of atomic energy levels. In the 1940s, physicists noticed that certain energy levels in hydrogen were slightly shifted from where theory predicted they should be. This discrepancy became known as the Lamb shift. The explanation required acknowledging the role of vacuum fluctuations. The electron in a hydrogen atom interacts not only with the proton, but also with the fluctuating electromagnetic field of the vacuum. These interactions slightly alter the electron's energy. When calculations included this effect, the predictions matched the observations with astonishing accuracy. This was no longer philosophy. It was measurement. Another breakthrough came from experiments involving forces between neutral objects. According to classical physics, two uncharged metal plates placed near each other in a vacuum should feel no force at all. And yet, when physicists performed the experiment with extreme precision, they found a tiny attraction pulling the plates together. This effect, predicted by Hendrik Casimir in 1948, arises because the vacuum behaves differently between the plates than outside them. Certain vacuum fluctuations are suppressed in the narrow gap, creating a pressure imbalance. Empty space pushes back. These discoveries slowly reshaped the scientific picture of nothingness. The vacuum was no longer empty, no longer quiet. It was structured, energetic, and measurable. It influenced matter even when matter was absent. Importantly, this realization did not arrive all at once. It emerged gradually through careful experiments, reluctant equations, and results that could not be ignored. The vacuum revealed itself not by dramatic spectacle, but by subtle deviations from expectation. There is something fitting about that. The quantum vacuum does not announce itself loudly. It whispers through small corrections, tiny shifts, and faint forces. It is easy to overlook unless you listen closely. As you rest now, the same principles are quietly at work around you. The atoms in your body retain zero-point motion. The electromagnetic field around you fluctuates gently, even in darkness. the space between objects is never truly calm. This discovery also carried a philosophical weight that physicists did not seek but could not avoid. It blurred the boundary between something and nothing. The vacuum became a kind of background existence, not matter, not energy in the usual sense, but a necessary foundation for both. In time, this understanding would influence cosmology, particle physics, and even our ideas about the origin of the universe. If empty space contains energy, then it can shape cosmic expansion. If it fluctuates, it can seed structure. If it is unstable, it can change. But those deeper implications come later. For now, the second truth settles gently into place. Scientists did not discover the restless vacuum by imagining it. They discovered it because reality refused to be silent. At the lowest energies, at the coldest temperatures, at the deepest emptiness, motion remained. Nothingness, it turned out, was never truly nothing. And as we continue this quiet journey, one question naturally arises. If the vacuum always carries energy, is there a lowest possible calm, or does motion continue even deeper than we can measure? Part 3. 0-point energy and the lowest possible calm. Is there a true state of rest in the universe? Quantum mechanics says no. Even at the lowest energy state allowed by nature, called the ground state, motion remains. This unavoidable activity is known as 0-point energy. It means that particles can never be completely still, and neither can the space around them. The universe, it seems, does not permit perfect silence. To understand why this matters, it helps to imagine what scientists once hoped to find. For centuries, rest was treated as the natural endpoint of motion. A pendulum slows, a spinning wheel stops, heat dissipates. Given enough time and cooling, everything should settle into stillness. Absolute zero, defined as 0 Kelvin, became the symbol of that ultimate calm. At that temperature, all thermal motion should vanish. Nothing should move. Nothing should change. But when physicists approached this limit, both in theory and in experiment, they encountered something unexpected. Motion did not disappear. Instead, it softened, becoming subtle but persistent, like a breath that never fully fades. The reason lies at the heart of quantum mechanics. In this framework, particles are not tiny solid points following precise paths. They are described by wave functions, spread out entities with probabilities rather than certainties. A particle confined to a region of space cannot have both a perfectly defined position and zero momentum. This is not a practical limitation, it is a rule of reality. If a particle were brought to complete rest, its momentum would be exactly zero. The uncertainty principle forbids this unless its position becomes infinitely uncertain. In other words, a perfectly still particle would have to be everywhere at once. Nature does not allow such a state, and so, even in the calmest possible conditions, particles retain a minimum jitter, a gentle restlessness that cannot be removed. This residual motion carries energy, not thermal energy, which depends on temperature, but something deeper. 0-point energy is the energy that remains when all removable energy has been stripped away. It is the quiet floor beneath which systems cannot descend. One way physicists came to understand this was through the study of simple systems called quantum harmonic oscillators. These are idealized models that describe vibrations in atoms, molecules, and fields. In classical physics, an oscillator at rest has zero energy. But when the same system is treated quantum mechanically, the lowest allowed energy is not zero. It is half a quantum above it. That small offset appears everywhere. Atoms vibrate even at absolute zero. Molecules retain a faint trembling. Crystals never fully stop humming. And because fields can also be treated as collections of oscillators, the same principle applies to empty space itself. The electromagnetic field, for example, can be thought of as an infinite set of oscillators, one for each possible wavelength. Even when no light is present, each of these oscillators retains 0-point energy. The sum of all these tiny contributions fills the vacuum with a subtle, omnipresent energy. This does not mean that the vacuum is hot. 0-point energy does not radiate heat or raise temperature in the usual way. Instead, it forms a baseline, a constant background that defines what calm means in a quantum universe. As you breathe right now, the atoms in your lungs are vibrating slightly, not because of warmth alone, but because they cannot do otherwise. Even if the air were cooled to absolute zero, those vibrations would persist. Calm at the deepest level is not stillness, it is constrained motion. This realization changes how we think about rest itself. Rest is no longer the absence of movement, it is a balance, a minimum allowed activity shaped by the rules of nature. The universe does not allow its components to fully stop. It allows them only to settle into their gentlest possible motion. Zero-point energy also explains why certain systems behave the way they do. Without it, atoms would collapse, electrons would fall into nuclei, matter as we know it would not exist. The faint motion enforced by quantum mechanics provides stability. It prevents total collapse by keeping particles from occupying the same state. In this way, zero-point energy is not a nuisance or a technical detail. It is a quiet guardian of structure. It ensures that space has texture, that matter has size, and that emptiness has character. There is something deeply soothing about this idea. Even in the coldest, darkest regions of the universe, nothing is ever truly frozen. Activity continues, gentle and restrained. The cosmos does not snap into silence. It whispers instead. Physicists have measured the consequences of zero-point energy with remarkable precision. Atomic clocks, for example, must account for zero-point fluctuations to maintain accuracy. Superconductors behave as they do because electrons retain quantum motion even at extremely low temperatures. The stability of solids depends on it. And beyond matter, the vacuum itself responds. The zero-point energy of fields leads to measurable effects, like subtle forces and tiny shifts in energy levels. These effects are small, but they are consistent, repeatable, and real. Yet, zero-point energy also presents one of the greatest challenges in modern physics. When theorists calculate the total zero-point energy of all fields filling space, the number they obtain is staggeringly large, far larger than what we observe influencing the universe's expansion. This discrepancy, known as the vacuum energy problem, suggests that our understanding is incomplete. Still, the existence of zero-point energy itself is not in doubt. It has been confirmed again and again through experiment. The universe refuses to grant us a perfectly quiet state. From a human perspective, this may feel abstract. We are accustomed to thinking of calm as the absence of motion, a still lake, a silent room, a resting body. But at the deepest level, calm is something else entirely. It is motion, reduced to its most delicate form, bounded but unending. When you lie still at night, your body appears motionless, your breath slows, your heartbeat softens. Yet within you, atoms vibrate, electrons shift and fields fluctuate, not violently, not chaotically, just enough to remain real. The same is true of the space beyond your walls, beyond the atmosphere, beyond the stars. The vacuum between galaxies is not dead. It carries zero-point energy, quietly present, shaping what can exist. This lowest possible calm is not something the universe will ever leave behind. Even as it expands and cools over trillions of years, even as stars burn out and matter thins, zero-point energy will remain. It is not a phase, it is a condition, and that brings us to a gentle but profound realization. Silence, in the cosmic sense, does not mean nothing is happening. It means nothing is happening loudly enough for us to notice. Beneath that silence, activity continues, disciplined and subtle. As physicist Richard Feynman once reflected, the universe is not only stranger than we imagine, it is stranger than we can imagine. Zero-point energy is one of those strangenesses, quietly embedded in everything, asking us to reconsider what rest truly means. So when we ask whether there is a true state of rest in the universe, the answer is clear. There is a lowest calm, but it is not stillness. It is the softest possible motion allowed by the rules of reality. And as we drift onward in this quiet exploration, another question begins to rise. If energy is always present, even in the vacuum, how does it briefly take form as particles that appear and vanish from nothing at all? Part 4. Virtual particles and fleeting existence. what appears briefly and vanishes without a trace. In the quantum vacuum, particles can emerge from energy itself, existing only for unimaginably short moments before disappearing again. These are virtual particles, not directly observable, yet measurable through their effects. They borrow energy from the vacuum, live briefly, and return it, like ripples that never quite reach the surface. To understand how something can appear from what seems like nothing, we return once more to the quiet rules of quantum mechanics. At the smallest scales, energy and time are linked by uncertainty. The more precisely one tries to define energy, the less precisely one can define how long that energy exists. Over extremely short intervals, nature allows small violations of what would otherwise be forbidden, provided they are swiftly corrected. This is not chaos. It is bookkeeping. In this narrow window of allowance, the vacuum becomes active in a very particular way. Particle-antiparticle pairs can momentarily emerge, drawing energy from the vacuum's zero-point fluctuations. These pairs exist only for an instant, then annihilate each other, returning their borrowed energy as if nothing had happened. From a distance, the vacuum appears unchanged. But up close, it flickers with brief possibilities. These transient entities are called virtual particles. The word virtual can be misleading. It does not mean imaginary or unreal. It means indirect. Virtual particles cannot be isolated or detected as free particles, but their influence is real and measurable. They leave fingerprints on the behavior of matter, light, and forces. One way to picture this is to imagine calm water beneath a light breeze. From afar, the surface looks smooth, but at closer inspection, tiny ripples continuously form and fade. They do not travel far. They do not become waves, yet they are undeniably present. Virtual particles are like that, fleeting disturbances in an otherwise steady background. In quantum field theory, forces are explained through the exchange of particles. The electromagnetic force, for example, arises from the exchange of photons. But between charged particles, these photons are often virtual. They do not appear as flashes of light. They exist only within the interaction itself, carrying force without ever being directly seen. This means that even the forces holding your body together are mediated by things that briefly exist and then disappear. The stability of atoms, the rigidity of solids, the pressure of your chair against the floor all depend on interactions shaped by virtual particles flickering in and out of the vacuum. One of the earliest confirmations of this idea came from the behavior of the electron. According to simple theory, the electron should behave as a point particle with a fixed charge, but precise measurements revealed tiny deviations. The electron's charge and mass appeared slightly altered by its interaction with the vacuum itself. The explanation lies in virtual particles. The electron is constantly surrounded by a cloud of virtual particle-antiparticle pairs that briefly form around it. These fluctuations modify how the electron responds to forces. When physicists included these effects in their calculations, the predictions matched experiments to astonishing precision, often agreeing to more than 10 decimal places. This level of agreement is one of the greatest successes in the history of science. It tells us that virtual particles, fleeting though they are an essential part of how reality works. Another quiet demonstration comes from light itself. When a photon travels through what we think of as empty space, it is not moving through true nothingness. It passes through a vacuum alive with virtual particles. These particles can briefly interact with the photon, slightly altering its path or speed. The effect is incredibly small, but it exists. In extremely strong electromagnetic fields, these interactions become more pronounced. Under such conditions, light can even scatter off light, a phenomenon forbidden in classical physics, but allowed through virtual particle interactions. Again, what seems impossible becomes inevitable once the vacuum is understood as active. Virtual particles also play a role in one of the most poetic predictions of modern physics. Near the edge of a black hole, the intense curvature of spacetime affects the vacuum itself. According to theory, virtual particle pairs can form near the event horizon. Normally, they would annihilate almost immediately. But if one particle falls into the black hole while the other escapes, the pair is separated. The escaping particle becomes real, carrying energy away from the black hole. Over immense timescales, this process leads to what is known as Hawking radiation. A black hole, once thought eternal, slowly loses mass and evaporates, not because of anything inside it, but because the vacuum around it refuses to remain quiet. Here, the fleeting nature of virtual particles has cosmic consequences. The smallest fluctuations can shape the fate of the largest objects. Yet, despite their importance, virtual particles are not little objects popping in and out of existence like sparks. That image, while tempting, is only a rough metaphor. In the deeper mathematical description, they are internal elements of calculations, temporary states that help describe interactions between fields. Still, the language of appearance and disappearance captures something essential. The vacuum is not a static emptiness. It is a place where potential constantly brushes against reality, where existence is briefly sampled and then withdrawn. As you breathe right now, virtual particles are forming and vanishing in the space around you, within you, and through you. Not in any way that could disturb your rest, but in a manner so constant and gentle that it becomes the background of being. This realization brings with it a subtle shift in how we think about existence. Something does not need to persist to matter. Even the briefest presence can have lasting effects. In the quantum vacuum, what exists for less than a trillionth of a second can shape forces that endure for billions of years. There is also something deeply humbling here. Human intuition is built for solidity and duration. We trust what stays. But the universe, at its foundation, is comfortable with transience. It allows things to exist only briefly, to influence and then disappear, leaving no trace except in the structure of reality itself. Virtual particles are not an exception to the rules. They are an expression of them. They arise because the vacuum is energetic, because uncertainty is fundamental, and because fields never truly rest. This constant flicker does not make the universe unstable. On the contrary, it makes it resilient. The same fluctuations that seem chaotic at small scales average out at larger ones, producing the smooth, predictable world we experience. Calm emerges not from stillness, but from balance. When physicists describe the vacuum today, they often speak of it as the ground state of fields, a sea of lowest energy activity. Virtual particles are waves on that sea, rising and falling without ever breaking the surface. And so, what appears briefly and vanishes without a trace is not meaningless. It is part of the ongoing negotiation between possibility and reality, a reminder that even in emptiness, the universe experiments, moment by moment, with what could be. As we continue this quiet journey, another question naturally takes shape. If these fleeting particles can exert real forces, can empty space itself push, pull, and press on matter in ways we can measure directly? Part 5. The Casimir effect and pressure from nothing can empty space push back? When two metal plates are placed extremely close together in a vacuum, they experience a measurable force pulling them inward. This phenomenon, known as the Casimir effect, arises not from matter, but from the structure of the vacuum itself. It is one of the clearest demonstrations that empty space contains real, physical energy. At first glance, the idea seems almost impossible. Two objects, electrically neutral, suspended in a perfect vacuum with nothing between them. Classical physics predicts nothing should happen. No charge, no gravity worth mentioning, no contact. And yet, when the distance between the plates becomes small enough, a force appears, not imagined, not inferred, measured. The Casimir effect was predicted in 1948 by Dutch physicist Hendrik Casimir, who was studying the behavior of quantum fields between conducting surfaces. His insight was subtle and deeply quiet. The vacuum, he realized, is not the same everywhere. Boundaries matter. When you introduce surfaces into empty space, you change the way the vacuum can behave. To understand why, imagine again the vacuum as a sea of fluctuating fields. These fields can vibrate in many different modes, like strings capable of countless harmonics. In open space, all of these modes are allowed. The vacuum hums freely, its fluctuations spanning a wide range of wavelengths. But when two metal plates are brought very close together, something changes. Only certain wavelengths can fit between them. Long waves are excluded, shorter ones remain. Outside the plates, the vacuum still supports the full range of fluctuations. Inside the gap, it does not. This imbalance creates pressure. There are more vacuum fluctuations pushing from the outside than from the inside. The result is a net force that gently presses the plates together. Nothing is emitted, nothing flows. And yet, the plates move. The vacuum itself is doing the pushing. What makes this effect so remarkable is not just that it exists, but that it exists exactly as quantum theory predicts. The strength of the force depends only on fundamental constants, the area of the plates and the distance between them. No adjustable parameters, no hidden variables. When the plates are brought to within a few nanometers, the force becomes measurable and it matches the equations. This is not an abstract curiosity. The Casimir effect has been confirmed repeatedly in laboratories around the world. Using carefully controlled experiments, physicists have measured the force with high precision, refining techniques to isolate it from other influences. Each time, the result is the same. Empty space pushes back. There is something profoundly calming about this discovery. It does not overturn the universe. It does not shout. It simply reveals that the vacuum has texture, that boundaries shape reality, that nothingness responds to constraints. The Casimir effect also marks an important moment in the history of physics. It was one of the first clear demonstrations that zero-point energy and vacuum fluctuations are not just mathematical conveniences. They have mechanical consequences. They can move objects. They can do work. This realization reshaped how physicists think about space itself. The vacuum is no longer a passive background. It is an active participant, sensitive to geometry and configuration. Change the shape of space, and the vacuum responds. As you rest now, surrounded by walls, floors, and surfaces, the same principle quietly applies. The vacuum between objects is not identical to the vacuum far away. The presence of boundaries subtly alters which fluctuations are allowed. The effect is far too small to notice in everyday life, but it is always there. In the realm of nanotechnology, however, the Casimir effect becomes significant. At very small scales, it can cause tiny components to attract each other unexpectedly. Engineers designing microscopic machines must account for it. The vacuum, once ignored, becomes a force to manage. Yet even here, the tone remains gentle. The Casimir effect does not dominate. It does not overwhelm. It simply reminds us that at small distances, emptiness has structure. There's also a deeper lesson hidden in this phenomenon. The force between the plates does not come from particles bouncing back and forth. It comes from the absence of certain possibilities. By restricting what the vacuum can do in one region, we create an imbalance. Reality responds not just to what is present, but to what is missing. This idea appears again and again in modern physics. Energy depends on allowed states. Stability depends on constraints. The vacuum is defined not only by its contents, but by its limitations. In a quiet way, the Casimir effect teaches us that nothingness is relational. Empty space is not the same everywhere. It depends on context, on geometry, on proximity. Two regions of vacuum can behave differently simply because of what surrounds them. This challenges the old notion of absolute emptiness. There is no universal featureless void. There are only vacuum states shaped by conditions. Even gravity feels this influence. In curved spacetime, vacuum fluctuations behave differently than in flat space. Near massive objects, the structure of the vacuum shifts. Near horizons, it can give rise to radiation. In expanding space, it can influence cosmic evolution. The Casimir effect is a small, controlled window into this larger truth. It is the vacuum made tangible, pressure without matter, force without contact. There is also something reassuring in how subtle it is. The universe does not need violence to express its complexity. A force born from nothing can be gentle, precise, and predictable. The equations work. The measurements agree. Calm persists. As you breathe slowly, consider that the solidity of the world around you rests, in part, on these invisible interactions. The vacuum does not undermine stability. It supports it. It presses gently, consistently, shaping how matter arranges itself. The Casimir effect also invites a philosophical pause. If empty space can exert pressure, then the distinction between something and nothing becomes even thinner. The vacuum is not an absence waiting to be filled. It is a presence with its own properties, its own behavior. And yet, it remains quiet. You do not feel it. You are not disturbed by it. Its influence is woven so seamlessly into reality that it becomes part of the background calm. In the end, the Casimir effect does not shout that the universe is strange. It whispers that it is subtle, that even emptiness carries rules, that even nothing has boundaries. As we continue this gentle exploration, another question begins to form. If the vacuum behaves differently depending on conditions, what exactly is it made of at the deepest level? Are particles truly fundamental, or is there something even quieter beneath them all? Part 6. Fields beneath everything. If particles are not fundamental, what is? Modern physics suggests that fields are the true foundation of reality. Every particle is an excitation, a tiny vibration in an underlying field that fills all space. Even when no particles are present, these fields remain. The vacuum, then, is not empty at all. It is the quiet presence of everything that could exist. For much of human history, matter was imagined as something solid and indivisible. Tiny pieces stacked together to build the world. Atoms were once thought to be the final units, the smallest bricks of existence. Then atoms revealed electrons and nuclei. Nuclei revealed protons and neutrons. Protons revealed quarks. With each layer uncovered, the idea of a fundamental particle grew more fragile. Eventually, physics reached a turning point. Instead of asking what the smallest pieces were, scientists began asking a different question. What if particles are not pieces at all? In quantum field theory, the most successful framework ever devised for describing nature at small scales, particles are no longer treated as the foundation. Fields are. Each type of particle corresponds to a field that exists everywhere in space without exception. The electron field fills the entire universe. The quark fields fill it too. So does the electromagnetic field, the Higgs field, and many others. Particles, in this view, are not objects moving through empty space. They are localized disturbances in these ever-present fields. A particle is what happens when a field vibrates in a particular way, at a particular location, with a particular energy. This is a subtle but profound shift. It means that even when no particles are detected, the fields themselves are still there. The vacuum is simply the state where all fields are in their lowest possible energy configuration. Nothing is turned off. Nothing disappears. The universe does not empty itself. It merely becomes quiet. To picture this, imagine an ocean on a calm night. When the surface is smooth, no waves are visible, but the water itself is still there, stretching endlessly beneath the surface. A wave is not something added to the ocean. It is a motion of the ocean. In the same way, a particle is not something added to space. It is a motion of a field that already fills space. This analogy is imperfect, but it captures the essence. Fields are not located inside space. They are space's content. They define what space can do. One of the most striking confirmations of this idea came with the discovery of the Higgs field. Unlike other fields, which can exist at zero value in the vacuum, the Higgs field has a non-zero value even in empty space. The entire universe is permeated by it. Particles moving through this field acquire mass not because they collide with anything, but because they interact with the field's constant presence. This means that mass itself is not an intrinsic property of particles. It is a relationship between particles and a field that fills all space. Without that field, the universe would look very different. Particles would move at the speed of light. Atoms would not form. Chemistry would not exist. The vacuum, in this sense, is not a neutral background. It is an active environment that gives particles their identities. Even fields that do vanish in the vacuum do not truly disappear. They retain their ability to fluctuate. As we explored earlier, zero-point energy ensures that no field can be perfectly still. Every field has a baseline activity, a faint trembling that persists even in the absence of particles. This is why the vacuum can give rise to virtual particles. It is not creating something from nothing. It is rearranging its own underlying activity into brief, localized forms. From this perspective, emptiness becomes possibility. The vacuum is not a lack of content. It is a state rich with potential. Every particle that has ever existed, every interaction that has ever occurred, emerged from fields already present. As you sit quietly now, the space around you is filled with these fields. They pass through your body without resistance. They are not blocked by walls or matter. They simply are. Your atoms are patterns within them. Your solidity is a stable configuration of field excitations. There is something deeply calming about this picture. It suggests continuity beneath change. Particles appear and disappear. Structures form and dissolve, but the fields remain steady and universal, supporting all these transformations. This framework also helps explain why the laws of physics are the same everywhere. Because the fields are everywhere. An electron behaves the same way on Earth as it does in a distant galaxy, because the electron field is the same field, filling all of space uniformly. The vacuum, then, is not an absence of reality. It is the most symmetric, uniform expression of it. Yet, fields are not static entities. They interact with one another. They can influence, couple, and reshape each other. The vacuum itself can change under extreme conditions. In the early universe, as temperatures cooled and symmetries broke, fields settled into new configurations. These transitions shape the forces and particles we observe today. In this way, the vacuum has a history. It is not timeless. It has evolved along with the universe, carrying the imprint of cosmic events long past. There are even theories suggesting that multiple vacuum states may exist, each corresponding to different configurations of fields. Our universe may occupy one such state, stable but not unique. The laws of physics we experience could be a consequence of how the vacuum fields happen to settle. This idea remains speculative, but it reinforces the central theme. What we call empty space is deeply structured. It is governed by rules. It has properties. It influences outcomes. When physicists probe reality at ever smaller scales, they do not find a hard floor of indivisible particles. They find layers of description that grow more abstract and more unified. Fields replace particles, relationships replace objects, motion replaces substance, and still the experience of the world remains calm and coherent. Chairs remain solid, the ground supports you, light behaves predictably. The underlying complexity does not disrupt the surface tranquility. That is the quiet elegance of this picture. The universe is not built from static pieces locked together. It is built from continuous entities capable of gentle motion and subtle change. Stability emerges not from rigidity, but from balance. As you rest, consider that the emptiness around you is not void. It is the quiet presence of all fields in their calmest state. It is the ocean beneath the waves, the fabric beneath the pattern. Nothing needs to happen for this to be meaningful. The vacuum does not require events to justify its existence. It is enough that it is there, supporting everything else. And as we move forward in this exploration, another question naturally unfolds. If fields fill all space and define what can exist, how do their constant fluctuations shape the structure of the universe on the largest scales? Part 7. Quantum fluctuations and the flicker of reality. Why does the universe never fully settle? Quantum fluctuations are spontaneous, unpredictable changes in energy that occur even in empty space. They are not caused by anything external. They simply happen. These fluctuations give the vacuum its restless character and may have played a crucial role in shaping the structure of the cosmos itself. At first, this idea feels deeply counterintuitive. In everyday life, change has a cause. A breeze moves leaves, heat makes atoms vibrate, sound comes from motion. We are used to tracing activity back to something that disturbed a system. But at the quantum level, this logic quietly breaks down. The vacuum does not need to be touched to respond. It is never perfectly still to begin with. Quantum fluctuations arise from the same principle that underlies zero-point energy and virtual particles. The uncertainty principle does not merely limit what we can measure, it enforces a kind of intrinsic motion. Energy cannot be pinned to a single fixed value everywhere at once. Over tiny regions of space and fleeting moments of time, energy must vary. These variations are the fluctuations. They are not rare events, they are constant. Every point in space experiences them all the time. The vacuum flickers, not dramatically, but persistently. A gentle shimmer beneath reality, invisible to our senses, yet foundational to how the universe behaves. One way to imagine this is to think of the vacuum as a perfectly stretched fabric. From afar, it looks smooth and uniform, but under extreme magnification, it reveals a fine, restless texture, not holes, not tears, just motion at the smallest possible scale. The fabric never lies flat. These fluctuations are random but not chaotic. Their behavior is governed by precise statistical rules. Over large scales, they average out, producing the calm, stable universe we experience. But on small scales, their influence is profound. Particles feel these fluctuations constantly. Fields respond to them. Forces emerge from them. Even the values of physical constants are subtly shaped by this restless background. One of the most remarkable consequences of quantum fluctuations is their role in the early universe. When the universe was unimaginably young, space itself was expanding rapidly. During this period, known as cosmic inflation, tiny quantum fluctuations in energy were stretched to astronomical scales. What began as minuscule variations in the vacuum became the seeds of galaxies, clusters, and the large-scale structure of the cosmos. Regions that were slightly denser due to fluctuations attracted more matter. Over billions of years, gravity amplified these differences, turning faint irregularities into stars and galaxies. In this sense, everything you see in the night sky traces its origin back to the vacuum's smallest flickers. The distribution of galaxies is not random noise. It is the fossil record of quantum fluctuations made visible. Even the cosmic microwave background, the faint afterglow of the Big Bang, carries this imprint. Its tiny temperature variations map the early fluctuations of the vacuum with extraordinary precision. Satellites have measured these patterns, confirming that the universe's structure grew from quantum beginnings. This connection between the smallest scales and the largest structures is one of the most calming insights in modern science. It tells us that nothing is isolated, that the quietest motions can echo across cosmic distances, that the universe grows not from perfect uniformity, but from gentle imperfection. Quantum fluctuations are also responsible for why absolute emptiness is impossible. If space were perfectly uniform and unchanging, it would violate the rules of quantum mechanics. The vacuum must fluctuate. Stillness is not an option, yet these fluctuations do not make the universe unstable. They are balanced. For every upward variation in energy, there is a downward one. Over time and space, equilibrium holds. The universe remains coherent, predictable, and safe. As you rest now, these fluctuations continue around you, not in a way that could disturb your calm, but in a way that quietly sustains existence. The atoms in your body owe their stability to the same quantum rules that allow the vacuum to flicker. There is something deeply reassuring in this. Reality does not require constant correction to remain intact. Its smallest motions naturally support its largest structures. The flicker is not a flaw, it is a feature. Quantum fluctuations also blur the line between potential and reality. A fluctuation is not yet a particle, not yet an event, but it is more than nothing. It is a possibility briefly expressed. Most of these possibilities fade without consequence. Some, under the right conditions, are amplified into something lasting. This is how the universe explores what it can become, not through intention or design, but through constant, gentle variation constrained by law. Importantly, these fluctuations are not signs of randomness in the everyday sense. They are unpredictable, but not arbitrary. Their statistical properties are precise. The universe knows how much it is allowed to flicker, and no more. In laboratory experiments, physicists can observe the effects of quantum fluctuations directly. They appear as noise in ultrasensitive measurements, they limit how quiet a signal can be. Even the most carefully isolated systems encounter a fundamental flaw of uncertainty. This is why absolute silence cannot be engineered. There is always background activity, even when all external disturbances are removed. The vacuum itself sets the limit. Yet again, this limit is gentle. It does not overwhelm. It defines a baseline. Just as zero-point energy defines the lowest calm, fluctuations define the texture of that calm. From a philosophical perspective, quantum fluctuations invite a quiet shift in how we think about causation. Not everything that happens needs a cause in the classical sense. Some things happen because the rules allow them to, because reality, at its foundation, is not static. This does not make the universe unpredictable in a threatening way. It makes it adaptable. It allows complexity to arise without fragility. Order emerges not despite fluctuation, but because of it. When you breathe slowly and let your thoughts drift, your mind mirrors this structure. Calm does not mean the absence of thought. It means thoughts arise and fade without disturbance. The universe behaves in a similar way. Fluctuations arise and fade, leaving behind a stable whole. The flicker of reality is constant, but it is also contained. It does not grow louder over time. It does not spiral out of control. It remains part of the background rhythm. As we look deeper into the nature of the vacuum, we find that this flicker is not something to fear or eliminate. It is something to understand. It is the reason the universe can change, evolve, and exist at all. If everything were perfectly uniform, nothing could happen. No structure could form, no time could pass. The universe would be frozen in sameness. Quantum fluctuations prevent that fate. They ensure that reality remains dynamic even in its calmest state. And so, the universe never fully settles, not because it is unstable, but because it is alive at the deepest level allowed by physics. As we continue this quiet journey, another question gently emerges. If these fluctuations shape reality on every scale, how did they influence the very beginning of the universe, when everything was closer, hotter, and more tightly bound than we can imagine? Part 8. The Vacuum and the Birth of the Universe. Could everything have come from almost nothing? In the earliest moments after the Big Bang, the energy of the vacuum may have driven a rapid expansion of space itself. This process, known as cosmic inflation, smoothed the universe while seeding tiny irregularities that later became galaxies. The quiet energy of the vacuum may be the reason anything exists at all. When we trace the universe backward in time, everything grows denser, hotter, and closer together. Galaxies collapse into points, atoms dissolve, even protons and neutrons lose their identity. Eventually, we arrive at a moment so early that our familiar laws of physics begin to blur. This is not a place we can visit directly. It is a boundary we approach through mathematics, observation, and careful inference. For much of the 20th century, the Big Bang was imagined as a simple expansion from an initial hot, dense state. Space grew, matter cooled, light decoupled, structures slowly formed. But as cosmologists refined their models, troubling questions appeared. Why does the universe look almost the same in every direction? Why is space so flat, so close to geometric balance? And why were the initial conditions so delicately arranged? These puzzles led physicists to consider a deeper role for the vacuum itself. Cosmic inflation proposes that, in the earliest fraction of a second after the Big Bang, space underwent an extraordinary burst of expansion, not a slow stretching, but an exponential one. In an instant, regions smaller than an atom grew to astronomical scales. This expansion was driven not by matter or radiation, but by vacuum energy. During inflation, the vacuum behaved very differently from how it does today. Its energy density remained nearly constant even as space expanded. This property caused space itself to accelerate outward, smoothing away irregularities and flattening curvature. Tiny regions that were once in close contact were rapidly pulled apart, explaining why distant parts of the universe appear so similar. This is one of the most remarkable aspects of the vacuum. Under the right conditions, it does not merely sit quietly in the background, it can shape the geometry of the universe. Yet inflation did more than smooth, it also amplified the vacuum's smallest fluctuations. As space expanded, quantum fluctuations that normally exist only at microscopic scales were stretched across vast distances. What began as tiny variations in energy became imprinted into the structure of space-time itself. These stretched fluctuations became the seeds of everything that followed. Where the vacuum fluctuated slightly upward in energy, matter would later collect. Where it fluctuated downward, less matter would gather. Over billions of years, gravity magnified these differences, turning faint variations into stars, galaxies, and clusters. The universe's large-scale structure is a direct descendant of the vacuum's earliest whispers. This idea is not speculation alone. It is supported by precise observations. The cosmic microwave background, the faint afterglow of the Big Bang, carries a detailed map of these primordial fluctuations. Satellites have measured their size, distribution, and pattern. The results align remarkably well with predictions from inflationary theory. What we see when we look deep into space is not randomness, it is the memory of the vacuum in its earliest state. There is something quietly profound here. The universe did not begin as a perfectly smooth, lifeless expansion. It began with gentle imperfections, with subtle imbalance, with quantum uncertainty woven into its foundation. Without these tiny irregularities, matter would never have clumped, stars would never have ignited, life would never have emerged. In this sense, the vacuum was not merely present at the birth of the universe. It was creative. This does not mean the vacuum chose anything. There was no intention, no direction, only lawful behavior under extreme conditions. The same quantum rules that govern fluctuations today operated then, but their effects were magnified by rapid expansion. The vacuum provided both calm and variation, smoothness on large scales, structure on small ones, a balance that allowed complexity to unfold. As inflation ended, the vacuum's energy changed form. It decayed into particles and radiation, filling the universe with the ingredients of matter. Space continued to expand, but at a gentler pace. The era of structure formation began. In this picture, the Big Bang is not the creation of matter from nothing in a simple sense. It is a transformation, a shift in how energy was arranged. The vacuum transitioned from a high-energy state to a lower one, releasing energy into particles and light. The universe did not emerge from absolute nothingness. It emerged from a vacuum with properties. This reframes the oldest of questions. Instead of asking why there is something rather than nothing, physics invites us to ask what kind of vacuum allows something to exist. The focus shifts from absence to structure. Even today, the vacuum continues to influence cosmic evolution. Observations show that the universe's expansion is accelerating. This acceleration is attributed to a form of vacuum energy often called dark energy. While its exact nature remains uncertain, its behavior resembles that of a vacuum with a small, persistent energy density. If this interpretation is correct, then the same quiet presence that shaped the universe's beginning is also shaping its future. The vacuum, then, is not confined to the past. It is not a relic. It is an ongoing participant in cosmic history. As you rest now, billions of years after the universe's birth, the same underlying fields still fill space. The same quantum rules still apply. The calm you feel is supported by structures that trace their origin back to fluctuations stretched across the cosmos. There is a deep continuity here. The earliest moments of existence are not disconnected from the present, they are embedded within it. The vacuum that once drove inflation is related to the vacuum that allows atoms to exist today. This continuity offers a kind of reassurance. The universe is not fragile. It did not balance precariously on a knife's edge. It unfolded from robust principles that continue to operate reliably. And yet, mystery remains. We do not fully understand why the vacuum behaved as it did during inflation. We do not know what set its energy scale or why it changed when it did. These questions sit at the frontier of physics, waiting quietly. What we do know is that the vacuum is capable of remarkable things. It can expand space, it can seed structure, It can transform energy into matter, all without noise, without spectacle, without breaking its own rules. In this way, the birth of the universe reflects the same theme we have seen again and again. The deepest forces are not loud, they are subtle. They work through balance, not disruption. When you look up at the night sky, you are seeing the aftermath of this quiet beginning. Each galaxy is a stretched imprint of a tiny fluctuation. Each star is a consequence of a vacuum that refused to be perfectly uniform. The idea that everything came from almost nothing is not a claim of magic. It is a recognition that nothing, as physics understands it, is not empty. It is structured, energetic, capable. And as we continue this gentle exploration, another question naturally arises. If the vacuum helped give birth to the universe, what role does it play in shaping its long-term fate as space continues to expand into the deep future? Part 9. Dark Energy and the Expanding Void. Why is the universe expanding faster and faster? Observations show that space itself is accelerating outward, driven by something scientists call dark energy. One possibility is that this mysterious force is linked to the energy of the vacuum. If so, empty space is not just active, but powerful enough to shape the fate of the entire cosmos. For much of the 20th century, cosmologists believed the universe's expansion should be slowing down. Gravity, after all, pulls matter together. Galaxies attract one another. Over time, this mutual pull was expected to act like a brake, gradually reducing the speed at which space expands. The universe might coast, slow, or even collapse back inward. That was the quiet expectation. Then, in the late 1990s, astronomers looked carefully at distant supernovae, exploding stars so bright they can be seen across billions of light years. These stellar beacons act as cosmic mile markers, allowing scientists to measure how fast the universe has been expanding at different times in the past. What they found was deeply surprising. The expansion was not slowing down, it was speeding up. The farther away the supernovae were, the faster space appeared to be stretching between them and us. Something unseen was pushing the universe apart, overcoming gravity on the largest scales. This discovery was so unexpected that it reshaped modern cosmology almost overnight. To explain it, physicists introduced a new term, dark energy. Not because it is dark in any literal sense, but because its nature is unknown. It does not emit light, it does not clump into structures, it does not behave like matter or radiation. It reveals itself only through its effect on the expansion of space. One of the simplest explanations for dark energy is also one of the most subtle. It may be the energy of the vacuum itself. In Einstein's equations of general relativity, energy and pressure influence how space bends and evolves. A peculiar feature of vacuum energy is that it exerts negative pressure. Instead of pulling inward like gravity, it pushes outward. When space contains a small, uniform energy density of this kind, the result is accelerated expansion. This idea is not new. Einstein himself introduced a term like this, known as the cosmological constant, to keep the universe static in his original equations. When expansion was later discovered, he reportedly called it his greatest mistake. Yet decades later, a similar term returned, not to stop expansion, but to explain its acceleration. If dark energy is indeed vacuum energy, then the emptiest regions of space are the most influential. As the universe expands and matter becomes more spread out, the relative importance of vacuum energy grows. Galaxies drift farther apart, the voids between them widen, and in those voids, the vacuum quietly dominates. There is something almost poetic about this. As the universe grows older and more dilute, emptiness becomes the driving force, not matter, not light, but the background itself. The measured value of dark energy is small, extremely small. In everyday terms, it is negligible. A region the size of your room contains far less dark energy than the mass of a single grain of dust. And yet, because it is spread uniformly across all of space, its total effect is immense. Given enough distance, it overwhelms everything else. This uniformity is key. Dark energy does not clump or gather. It does not form structures. It remains evenly distributed as space expands. In fact, its density stays nearly constant even as the universe grows larger. This is the opposite of matter and radiation, which thin out as space expands. As a result, dark energy becomes more dominant over time. In the early universe, matter and radiation ruled. Today, dark energy accounts for roughly 70% of the total energy content of the cosmos. In the far future, it may approach 100%. If this trend continues, the universe's fate becomes clearer. Galaxies beyond our local group will drift beyond the reach of observation. Their light will stretch and fade. Eventually, they will slip beyond the cosmic horizon, no longer able to communicate with us even in principle. The universe will grow darker and quieter, not because matter disappears, but because space expands too quickly for light to keep up. And yet, even in this future, the vacuum remains. Its energy does not diminish. Its presence does not fade. It continues to drive expansion, steady and relentless. There are alternative explanations for dark energy. Some physicists propose new fields that evolve over time. Others suggest modifications to gravity itself on large scales. These ideas are actively studied, but so far the simplest explanation fits the data remarkably well. A small, constant vacuum energy appears sufficient to explain what we observe. This simplicity is both elegant and unsettling. It is elegant because it requires no new moving parts. The vacuum, already present everywhere, simply behaves as it does. It is unsettling because theoretical calculations of vacuum energy predict values vastly larger than what we measure. Somewhere between theory and observation, an enormous cancellation must occur. This discrepancy, known as the cosmological constant problem, is one of the deepest unsolved puzzles in physics. It suggests that we are missing something fundamental about how vacuum energy works. Still, the effect itself is real. Space is accelerating, the universe is expanding faster with time, and the vacuum is a leading candidate for why. As you rest now, it may be comforting to know that this expansion does not affect you. The atoms in your body are held together by forces far stronger than cosmic expansion. Even galaxies remain bound internally. The expansion only becomes noticeable across immense distances where gravity's grip weakens. The calm you feel is not threatened by this cosmic motion. Expansion happens gently, smoothly, without tearing or turbulence. Space stretches, but locally, everything remains stable. This contrast between local calm and global change is one of the universe's defining features. On small scales, structure persists. On large scales, emptiness takes over. There is also a philosophical softness to this idea. The future of the universe may be shaped not by dramatic collisions or violent endings, but by quiet persistence, by a gentle pressure exerted by empty space itself. Dark energy does not roar. It does not flash. It does not announce its presence. It simply acts uniformly and patiently, shaping the long-term destiny of everything that exists. In this sense, the vacuum is not just the birthplace of the universe, it is its guide through time. It sets the tempo of cosmic evolution, from the first moments after the Big Bang to the farthest reaches of the future. When we speak of the expanding void, we are not describing a hollow emptiness swallowing matter. We are describing a universe where space itself is dynamic, energized, and influential, where nothingness, properly understood, carries weight. As the universe continues to expand, questions remain open. Will dark energy remain constant forever? Could it change? Could it fade, reverse, or transform? These possibilities are still under study. Each carries a different vision of the cosmos's ultimate fate. But whatever the answer, one truth has already settled into place. Empty space is not passive. It shapes reality on the largest scales, it governs the motion of galaxies, it defines horizons and futures. And as we continue this quiet journey, another question naturally arises. If the vacuum can influence the universe so profoundly across billions of years, what happens to it under the most extreme conditions where gravity bends space to its limits? Part 10. The vacuum near black holes. What happens to nothing near the most extreme objects in existence? Near a black hole, the quantum vacuum behaves in surprising ways. According to theory, particle pairs can form at the edge of the event horizon, with one falling in and the other escaping as Hawking radiation. Even black holes, it seems, slowly evaporate because the vacuum never truly rests. Black holes are often described as regions where everything ends. Matter falls in. Light cannot escape. Time appears to slow to a halt at the boundary. From a distance, they seem like perfect sinks, swallowing anything that comes too close and giving nothing back. For many years, this image felt complete. A black hole was thought to be the ultimate one-way door in the universe. But when quantum physics is invited into the story, that stillness begins to crack. To understand why, it helps to picture the boundary of a black hole, known as the event horizon. This is not a solid surface. It is an invisible threshold in space-time. Cross it, and escape becomes impossible. Remain outside, and you are still part of the observable universe. The event horizon is a line drawn not in space alone, but in time. Near this boundary, gravity becomes extreme. Space-time is curved so sharply that the usual separation between past and future begins to blur. And it is here, at this delicate edge, that the vacuum reveals one of its most remarkable behaviors. As we have seen, the vacuum is never truly empty. Even in calm regions of space, quantum fluctuations constantly give rise to brief particle-antiparticle pairs. Under ordinary conditions, these pairs appear and annihilate almost instantly, leaving no trace. Energy is borrowed and returned so quickly that the balance holds, but near a black hole, the rules shift. When a particle pair forms very close to the event horizon, gravity can separate them before they annihilate. One particle may fall inward, crossing the horizon. The other may escape outward into space. The pair is broken. What was virtual becomes real. The escaping particle carries energy away from the black hole. To an observer far away, this appears as radiation emitted by the black hole itself. This phenomenon is known as Hawking radiation, named after the physicist Stephen Hawking, who first described it in the 1970s. This idea was startling when it was proposed. Black holes, the darkest objects in the universe, emitting radiation, not from their interiors, but from the behavior of the vacuum at their edges. What makes this effect so gentle is its scale. For stellar mass black holes, Hawking radiation is extraordinarily weak. The temperature associated with it is far colder than the cosmic background. Any radiation they emit is drowned out by the warmth of the universe around them. In practice, such black holes gain more energy from their surroundings than they lose. But over immense spans of time, the balance changes. As the universe expands and cools, the background temperature drops. Eventually, in a far future where stars have burned out and space has grown cold, black holes will begin to lose more energy than they gain. Very slowly, almost imperceptibly, they will shrink. Given enough time, even the largest black holes will evaporate completely. This is not a violent process. It does not end in an explosion. It is more like a slow exhale, stretched across trillions upon trillions of years. A gradual fading driven by the quiet persistence of the vacuum. There is something deeply humbling in this. Black holes, once thought eternal, are not immune to the rules of quantum reality. The vacuum reaches everywhere. Even the strongest gravity cannot silence it. From a theoretical standpoint, Hawking radiation arises because the definition of a vacuum depends on the observer. What looks like empty space to someone far away does not look the same to someone accelerating near a horizon. The vacuum is not absolute, it is contextual. This observer dependence is a subtle but profound feature of quantum field theory in curved spacetime. It tells us that emptiness is not a universal condition. It depends on motion, gravity, and perspective. Near a black hole, the vacuum for a distant observer contains particles. For an observer falling freely across the horizon, it may appear calm. Reality shifts with viewpoint, and the vacuum adapts accordingly. This leads to some of the deepest puzzles in modern physics. What happens to information that falls into a black hole? If black holes evaporate, does the information disappear forever, or is it somehow preserved in the radiation? These questions remain open, quietly debated, gently unresolved. What matters for our journey is this: the vacuum does not simply exist alongside black holes. It interacts with them, it shapes their behavior, it limits their permanence. As you rest now, far from any black hole, the same principles apply in a gentler form. The vacuum around you fluctuates, but gravity is weak. Particle pairs form and vanish without consequence. Near a black hole, gravity amplifies these effects, turning fleeting fluctuations into lasting change. This amplification is a recurring theme in physics. Extreme conditions do not introduce new rules, they reveal what the existing rules can do. The vacuum near a black hole is not fundamentally different from the vacuum elsewhere. It is the same set of fields, the same quantum laws. What changes is the environment. The curvature of space-time stretches the rules to their limits. In this way, black holes act as laboratories for the deepest questions about reality. They force quantum mechanics and general relativity to coexist. They expose the vacuum's hidden flexibility. There is also a quiet poetry in the idea that black holes evaporate not because of what they contain, but because of what surrounds them. The vacuum, patient and persistent, slowly reclaims energy from even the darkest objects. Nothing needs to collide, nothing needs to break. The process unfolds gently, governed by probability and time. If the universe lasts long enough, black holes will not dominate the future. Emptiness will. A thin, cold, expanding space filled with low-energy radiation and a calm vacuum that continues to fluctuate, even as structure fades. This does not make the universe bleak, it makes it consistent. The same vacuum that allowed structure to form ensures that no structure is truly eternal. Change is built in, but it is never abrupt. When we imagine black holes as ultimate endings, we project our own ideas of finality onto them. Physics suggests something softer. They are transitions, long-lived, powerful, but not permanent. The vacuum ensures that nothing is completely frozen, not even space-time itself. As we move forward, this realization deepens our understanding of emptiness. The vacuum is not just the quiet stage on which events play out. It is an active participant, shaping beginnings and endings alike. And as we continue this calm exploration, another question gently arises. If the vacuum can change behavior near horizons and under extreme gravity, can it itself exist in different states? And if so, what would it mean for reality if those states were to change? Part 11. Can the vacuum be changed? Is empty space always the same everywhere? In quantum field theory, different regions of space can exist in different vacuum states, each with its own energy level. Transitions between these states could reshape reality itself. Some physicists even speculate that the universe could, in theory, tunnel into a lower energy vacuum, rewriting the laws of physics in an instant. At first, this idea sounds unsettling. We tend to imagine the vacuum as a single uniform background, the same everywhere and forever. Empty space feels like the most stable thing imaginable. But modern physics suggests a more nuanced picture. The vacuum is not a single condition, it is a family of possibilities. To see why, we return to the idea of fields. Every field that fills space has a range of configurations it can occupy, each associated with a certain energy. The lowest energy configuration is called the vacuum state of that field. But lowest does not always mean unique. Some fields can have multiple local minima, different vacuum states that are stable under small disturbances, but not absolutely minimal. A useful way to imagine this is to picture a landscape of hills and valleys. A ball rolling downhill will settle into the nearest valley it encounters. That valley is stable. Small nudges won't dislodge the ball. But somewhere else in the landscape, there may be a deeper valley. The ball is not in the lowest possible state overall. It is in a local calm, not the deepest one. In physics, such a situation is called a metastable vacuum. Our universe, according to some theories, may occupy one of these metastable states. The fields that define reality may have settled into a configuration that is stable enough to last for billions of years, but not the absolute lowest energy configuration possible. This does not mean change is imminent. On human timescales, and even cosmic ones, such a vacuum is effectively permanent. But in principle, quantum mechanics allows for something extraordinary. The vacuum could transition to a lower energy state through a process known as quantum tunneling. Quantum tunneling is another example of the universe's gentle refusal to obey classical intuition. In classical physics, a system trapped in a valley cannot cross a hill without enough energy to climb it. In quantum mechanics, there is a small probability that it can appear on the other side without ever passing over the top. The barrier is not climbed, it is bypassed. If the vacuum were to tunnel to a lower energy state, the consequences would be profound. The values of fundamental constants could change, the masses of particles might shift, forces could behave differently. Atoms, chemistry, and even space-time itself might no longer exist in their current forms. Importantly, this is not something that would happen gradually. Such a transition, if it occurred, would propagate at the speed of light, altering the vacuum state as it spread. Inside the expanding region, the laws of physics would be different. Outside, everything would remain unchanged until the boundary arrived. This idea can feel dramatic, but it is not presented as a prediction. It is a theoretical possibility, one that arises naturally from the mathematics of quantum field theory. There is no evidence that such a transition is likely or even possible within the lifetime of the universe. Current measurements suggest that if our vacuum is metastable, its lifetime is vastly longer than the age of the cosmos. In other words, this is not a cause for worry. It is a reminder of how rich and flexible the concept of emptiness has become. What matters for our understanding is this: the vacuum is not just empty space stripped of content. It is a state defined by the configuration of fields. Change the configuration, and you change the vacuum. Change the vacuum, and you change what can exist. We have already seen smaller examples of this idea. In the early universe, as temperatures dropped, fields transitioned between different vacuum states. These transitions shaped the forces and particles we observe today. The breaking of symmetries gave rise to distinct interactions. The vacuum did not remain fixed, it evolved. Even today, in laboratory conditions, physicists can create regions that behave like different vacuum states. In superconductors, for example, electrons form a collective state that alters the behavior of the electromagnetic field within the material. The vacuum inside the superconductor is not the same as the vacuum outside. Fields behave differently. Resistance disappears. These are not changes to the universe at large, but they demonstrate a crucial principle. Vacuum states are physical. They can differ. They can be altered under the right conditions. On cosmic scales, the question becomes more philosophical. If the vacuum defines the laws of physics, then the laws we experience are not inevitable. They are contingent. They depend on which vacuum state the universe occupies. This does not diminish their reliability. Within a given vacuum state, the laws are stable and consistent, but it reframes them as emergent rather than absolute. There is a quiet humility in this realization. Reality may not be built on fixed rules handed down from outside. It may be shaped by the state of its own underlying fields. As you rest now, the vacuum around you feels calm and unchanging. And for all practical purposes, it is. The fields are settled. The constants are steady. The universe is reliable. But beneath that calm lies a deeper flexibility, one that only reveals itself in theory and in the most extreme conditions. Physicists continue to study whether our vacuum is truly stable or merely long-lived. Measurements of particle masses, especially that of the Higgs boson, provide clues. Some analyses suggest we may indeed live in a metastable vacuum, balanced delicately between configurations. Others argue for complete stability. The question remains open. What is certain is that the vacuum is not a passive backdrop. It is an active participant in defining reality's rules. There is also a comforting perspective here. Even if the vacuum could change, such a transition would not be random or chaotic. It would follow precise quantum laws. It would not be an accident. It would be an expression of the same principles that govern everything else. The universe does not harbor hidden traps or arbitrary endings. It unfolds according to rules that, while subtle, are consistent. In the meantime, the vacuum we inhabit continues to support a universe rich with structure, time, and meaning. Its current state allows stars to shine, atoms to bond, and consciousness to arise. That alone is remarkable. The possibility of other vacuum states reminds us that reality could have been different. But it also highlights how finely balanced the present state is, not fragile, but precise. As with so many themes in physics, the deepest truths are not loud. They do not announce themselves. They wait quietly in equations and implications, inviting reflection rather than fear. The idea that empty space can change does not undermine calm. It deepens it. It shows that stability is not the absence of possibility, but the presence of balance. And as we continue this quiet journey, another question gently presents itself. If the vacuum can exist in different states and carry energy, how does this invisible structure influence our experience of time itself, the steady flow we feel from moment to moment? Part 12. The Vacuum and the Arrow of Time. Why does time move forward? While the equations of physics often work the same backward and forward, the vacuum may play a role in defining direction. The way energy spreads, fluctuations decay, and fields settle may contribute to the universe's sense of before and after. Even time's flow may be tied to the behavior of empty space. At first glance, time feels obvious. Moments pass, causes precede effects. Memories point one way, never the other. Yet when physicists examine the fundamental laws that govern particles and fields, they encounter a quiet puzzle. Most of these laws make no distinction between past and future. They work just as well if time is reversed. A collision can run forward or backward in the equations without contradiction. And yet, reality clearly prefers one direction. Ice melts, but does not spontaneously reform. Stars burn fuel and fade. The universe expands rather than contracts. Something, somewhere, sets an arrow that points from what was to what will be. This arrow of time is one of the deepest mysteries in science. To approach it gently, we begin with the emptiest concept of equilibrium. Physical systems tend to move from less probable states to more probable ones. A drop of dye spreads through water. Heat flows from warm objects to cool ones. These processes define a direction not because of the underlying equations, but because of statistics. There are far more disordered states than ordered ones. This statistical tendency is known as the second law of thermodynamics, and it is often cited as the source of time's arrow. Entropy increases, disorder grows. The future is the direction of greater mixing. But this explanation raises another question. Why did the universe begin in such a low entropy, highly ordered state in the first place? Why was there an arrow to follow it all? This is where the vacuum quietly enters the story. In the earliest moments of the universe, as we explored before, the vacuum played a central role. Its energy drove inflation, its fluctuations seeded structure. But just as importantly, the vacuum defined a state of extraordinary order. Fields were arranged smoothly, fluctuations were small, entropy was low. This initial condition set the stage for everything that followed. As the universe expanded and cooled, fields transitioned toward more stable configurations, energy spread out, fluctuations decayed, the vacuum, in a sense, relaxed. This relaxation was not instantaneous. It unfolded over time, creating a natural direction from a more ordered vacuum state toward a less ordered one. Time's arrow may be linked to this gradual settling. Even today, the vacuum is not static. Quantum fluctuations arise and fade. Virtual particles appear and annihilate. Fields interact and return to equilibrium. These processes have a preferred direction. Fluctuations decay rather than grow without bound. Energy disperses. Calm is restored. This tendency toward equilibrium gives time its texture. Imagine a quiet room. A sudden sound echoes, then fades. The air vibrates, then stills. The process has a clear direction. The equations governing sound waves allow vibrations to increase or decrease, but the environment favors decay. Energy spreads out, becoming harder to localize. The vacuum behaves similarly, though far more subtly. Fluctuations do not accumulate indefinitely. They are smoothed out. The vacuum absorbs and redistributes energy in a way that defines a before and an after. Some physicists have suggested that time itself may be an emergent property arising from how the vacuum evolves. Rather than being a fundamental backdrop, time could be a measure of change in the vacuum's state. As fields relax and configurations shift, we perceive duration and sequence. In this view, time flows because the vacuum is not in perfect equilibrium and never has been. Its gradual evolution provides a direction. This idea resonates with cosmology. The expansion of the universe gives time a global arrow. Space grows, structures form, energy becomes more diffuse. The vacuum's role in driving expansion ties it directly to the universe's temporal direction. Dark energy, if it is vacuum energy, ensures that expansion continues. The future becomes a state of increasing separation, increasing dilution, increasing calm. The arrow of time points toward emptiness, not because emptiness is nothing, but because it is the most statistically likely outcome. Even the decay of unstable particles reflects this pattern. A particle in an excited state will eventually decay into a lower energy configuration, often releasing energy into the vacuum. The reverse process is possible in theory, but overwhelmingly unlikely. Again, the vacuum absorbs energy and smooths irregularities. From this perspective, the vacuum acts as a kind of reservoir. It receives energy, spreads it, and returns systems to balance. In doing so, it defines irreversibility. As you breathe now, you experience this arrow intimately. Air flows in and out, heat dissipates, thoughts arise and fade. Your body is constantly exchanging energy with its surroundings, including the vacuum that fills the space between atoms. These exchanges have direction. They are gentle, but they are not reversible. The vacuum's role here is quiet, but essential. It is the medium through which energy disperses. It is the backdrop against which fluctuations settle. Without it, there would be no environment for relaxation, no baseline toward which systems return. Some researchers have even proposed that the arrow of time is linked to the vacuum's quantum entanglement structure. As regions of space interact, their quantum states become entangled. Over time, this entanglement spreads, making it increasingly difficult to reconstruct past configurations. Information becomes distributed across larger scales. This spreading of entanglement mirrors the growth of entropy. And, once again, the vacuum is the stage on which it occurs. What is striking about these ideas is how gentle they are. Time does not rush forward because of a ticking mechanism. It flows because the universe relaxes, because imbalance gives way to balance, because fluctuations fade into calm. There is no cosmic clock hidden in the vacuum, counting seconds. There's only ongoing adjustment, moment by moment. This also helps explain why time feels different at different scales. In regions of intense gravity or high energy, such as near black holes or in the early universe, the vacuum behaves differently. Fields are far from equilibrium, fluctuations are amplified, time stretches, slows, or warps. Direction remains, but pace changes. In calmer regions, like the space you occupy now, the vacuum is close to equilibrium. Changes are slow. Time feels steady and uniform. The arrow of time, then, is not imposed from outside. It emerges from the universe's internal behavior, from how the vacuum responds to energy and disturbance. There is something deeply comforting in this picture. Time's flow is not a force pushing you forward. It is a settling, a gentle, unfolding toward calm. The future is not pulled toward chaos, but toward balance. Even as complexity arises, even as life evolves and consciousness emerges, the underlying trend remains. Energy spreads, fields relax, the vacuum absorbs. This does not make time meaningless, it makes it precious. Each moment is a unique configuration of fields and fluctuations that will never be repeated in exactly the same way. When a moment passes, it does not vanish. Its effects are woven into the vacuum's evolving state. Information disperses, influence spreads, the universe remembers in subtle ways. As we reflect on the arrow of time, the vacuum appears not as a passive void, but as a quiet guide. It does not dictate events, it provides direction. And as we continue this calm exploration, another question gently emerges. If the vacuum helps shape time and memory, does it also carry information itself, quietly storing traces of everything that has ever occurred within it? Part 13. Nothingness and information. Does the vacuum remember? In modern physics, information is deeply connected to reality. Some theories suggest that even empty space stores information in subtle ways, encoded in fields and fluctuations. The vacuum may not only contain energy, but memory, quietly recording the history of the universe in its structure. For much of scientific history, information was treated as an abstract concept, something humans recorded in books, symbols, or machines. Physics, by contrast, dealt with matter, energy, and motion. But over the last century, these boundaries have softened. Information has emerged as a fundamental ingredient of the physical world, woven into the behavior of particles, fields, and space-time itself. At the most basic level, information is about distinction. A system contains information if it can be in more than one state. A particle's position, a field's value, a fluctuation's pattern, each represents a choice among possibilities. To know which possibility is realized is to possess information. In this light, the vacuum begins to look very different. We once imagined empty space as featureless, identical everywhere, incapable of storing anything. But as we've seen, the vacuum is structured, it contains fields, it fluctuates, it responds to boundaries and curvature. And wherever there is structure, there is the potential to encode information. One of the earliest hints of this connection came from black hole physics. When matter falls into a black hole, it seems to disappear from the observable universe. If the black hole later evaporates through Hawking radiation, what happens to the information about what fell in? Does it vanish forever? This question, known as the black hole information paradox, shook the foundations of physics. The laws of quantum mechanics insist that information is never truly destroyed, yet black holes appeared to erase it. Resolving this tension forced physicists to rethink what space, time, and the vacuum can do. Over time, a quiet consensus began to form. Information is not lost, it is transformed. In many modern interpretations, information about everything that falls into a black hole is not stored deep inside it, but encoded at or near the event horizon in subtle correlations within the quantum vacuum itself. The boundary of the black hole becomes a kind of information surface where the vacuum records what has passed. This idea connects to a broader principle known as the holographic principle. It suggests that the information contained within a volume of space can be described by information encoded on its boundary. In other words, space may store its information on surfaces, not in volumes. If this principle holds, then the vacuum is not merely a backdrop, it is an archive. Even far from black holes, the vacuum may carry information in the correlations between its fluctuations. Quantum fields are not independent at every point, they are entangled. A fluctuation here is subtly linked to fluctuations elsewhere. These connections form a vast, invisible web, stretching across space. Entanglement is a kind of memory. It preserves relationships between systems even when they are separated. When two regions of space interact, their quantum states become correlated. As they move apart, those correlations remain encoded in the vacuum. Over time, as interactions accumulate, the vacuum's entanglement structure grows richer. Information spreads not by being copied, but by being shared across larger regions. This process is gentle, continuous, and irreversible in practice. From this perspective, the vacuum does not remember events in the way a mind remembers. It does not store narratives or images. It preserves correlations, patterns, and constraints. It remembers in the language of physics. The early universe offers a striking example. The tiny quantum fluctuations present during inflation left imprints that are still visible today in the cosmic microwave background. Space itself carries a record of conditions that existed nearly 14 billion years ago. The vacuum remembers, not consciously, but structurally. Even now, the arrangement of galaxies reflects information encoded in the vacuum's earliest state. The distribution of matter is not random. It follows patterns seeded long ago and preserved through cosmic evolution. On smaller scales, similar processes occur constantly. When particles interact, they exchange information. The vacuum mediates these exchanges, carrying correlations forward in time. Information is not localized to objects alone. It is distributed across fields in space. This view leads to a profound realization. Forgetting is not fundamental. Loss of information is an illusion created by complexity. When systems interact with the vacuum, their information becomes spread out, entangled with countless degrees of freedom. It becomes inaccessible but not destroyed. A whisper in a room fades, the sound waves dissipate, the air returns to calm. But in principle, the information about that sound is still present, distributed among the motions of molecules and fields. The vacuum has absorbed it. This is why time feels irreversible, not because information disappears, but because it disperses. Reconstruction becomes practically impossible. As you sit quietly now, your presence is subtly imprinting itself on the vacuum around you. Heat flows, photons scatter, fields adjust. None of this is dramatic, but it is real. The universe records interactions at every scale. The idea that empty space holds memory can feel unsettling at first, but there is also something deeply comforting in it. Nothing you do vanishes without a trace. Influence persists, even if it becomes diffuse. This does not mean the vacuum is watching or judging. It is not conscious. It simply obeys laws that preserve relationships. Memory emerges as a byproduct of structure. In modern theoretical physics, some researchers go even further. They suggest that space-time itself may emerge from patterns of quantum information. According to these ideas, geometry is not fundamental. It arises from how information is organized in the vacuum. Distance, in this view, reflects how strongly regions of space are entangled. Time reflects how these patterns change. The vacuum is not just a container for information, it may be built from it. These ideas remain speculative, but they reflect a growing intuition. Information is not an add-on to physics, it is part of its foundation. What does this mean for our understanding of nothingness? It means that emptiness is not a blank slate, it is a structured medium capable of encoding history. The vacuum carries the imprint of past interactions, not as stories, but as constraints and correlations that shape what can happen next. The present is not isolated from the past, it is conditioned by it. The vacuum structure reflects what has occurred, and that structure influences what is possible. This interplay gives the universe coherence. It ensures continuity. It allows cause and effect to remain linked even as systems evolve. When you think back on a memory, your brain reconstructs a pattern stored in its structure. The vacuum does something similar on a cosmic scale. It does not recall events, it constrains outcomes based on prior states. There is a quiet beauty in this parallel. Memory is not something separate from matter, it is how structure persists through change. As night deepens and your thoughts slow, it may be soothing to consider that you are embedded in a universe that remembers, not in words, but in patterns. The calm around you is not empty. It is rich with quiet history. The vacuum does not cling to the past. It carries it forward gently, diffusing it, integrating it, allowing new moments to arise without erasing what came before. And as we continue this gentle journey, one final question begins to form. If the vacuum holds energy, shapes time, and carries information, how much of it can we ever truly observe? And where do the limits of our understanding finally rest? Part 14. The limits of measurement. Can we ever truly observe the vacuum itself? Every attempt to measure empty space disturbs it. Instruments introduce energy, particles, and noise. What we know about the vacuum comes indirectly, through its influence on matter and light. This makes the quantum vacuum one of the most elusive subjects in all of science, known more by its shadows than its form. From the very beginning of experimental physics, measurement has carried a quiet paradox. To observe something, you must interact with it. You must shine light, apply force, or place a detector in its path. And in doing so, you inevitably change what you are trying to observe. This is true for everyday objects, but at the quantum level, it becomes unavoidable. The vacuum is the most extreme example of this limitation. If you wish to study empty space, you must introduce something into it. A probe, a particle, a field. The moment you do, the vacuum is no longer alone. It responds, it fluctuates differently, it reveals itself only through reaction. This is why we never see the vacuum directly. We infer its existence from effects, from tiny forces between plates, from shifts in atomic energy levels, from subtle noise in precision experiments. The vacuum announces itself not by appearance, but by consequence. Quantum mechanics formalizes this limitation. The act of measurement is not passive. It alters the state of the system. There is no way to extract information without leaving a trace. For particles, this is expressed through uncertainty. For the vacuum, it is even more profound. To measure vacuum fluctuations, for example, physicists often observe how they affect something else. A mirror feels pressure. An atom experiences a shift. A photon changes course. The vacuum remains unseen, but its fingerprints accumulate. Even the most sensitive instruments are bounded by this rule. Gravitational wave detectors, designed to measure distortions in space-time smaller than the width of a proton, encounter a fundamental noise floor. Some of that noise comes not from the environment, but from quantum fluctuations in the vacuum itself. The act of measuring space-time is limited by the vacuum's own restlessness. This is not a failure of technology. It is a property of reality. The deeper physicists look, the more indirect their knowledge becomes. We cannot extract the vacuum, isolate it, or hold it still. We can only learn how it behaves when gently disturbed. There is something almost philosophical about this. The vacuum, the foundation of everything, resists being turned into an object. It is not something we can point to. It is something we live within. Even our most precise theories rely on mathematical descriptions rather than direct images. Quantum fields are not things we can see. They are functions, equations, relationships. The vacuum is defined by how these fields behave in their lowest energy state. It exists more clearly in mathematics than in perception. This does not make it unreal. It makes it subtle. Throughout the history of physics, some of the most important discoveries came from accepting such limits. Scientists learned that there are boundaries to what can be known directly: position and momentum, energy and time, field and measurement. Each pair carries uncertainty. The vacuum sits at the center of these boundaries. Even attempts to define a perfect vacuum encounter obstacles. In practice, laboratories can never remove all particles. Cosmic rays pass through, thermal radiation leaks in, fields fluctuate. Absolute emptiness remains an ideal, approached but never reached. Yet even if we could remove every particle, the vacuum would still not be silent. Zero-point energy would remain, fluctuations would persist, measurement would still disturb. This teaches us something gentle and important. The universe does not reveal itself all at once. It offers hints, it allows inference, it invites patience. There is a parallel here with human experience. Some things are known not by direct inspection, but by their influence. Calm is felt when noise fades. Gravity is sensed through weight. Love is known through effect, not observation. The vacuum belongs to this category. It is felt through how it shapes the world. In modern physics, this has led to a shift in how knowledge is valued. Instead of asking what something is in isolation, physicists ask how it behaves, what it does, how it interacts. The vacuum is defined operationally by its responses. This approach has been remarkably successful. It has allowed physicists to predict phenomena long before they were measured. The Casimir effect, Hawking radiation, the Lamb shift. Each was inferred from theory and confirmed indirectly. Still, the vacuum remains incomplete in our understanding. We do not know why its energy has the value it does. We do not know how it fits into a complete theory of quantum gravity. We do not know whether spacetime itself is continuous or discrete at the smallest scales. These unknowns are not failures, they are invitations. The limits of measurement do not close the door to knowledge, they define its shape. They tell us where humility is required. They remind us that some aspects of reality may always remain just beyond direct reach. As you rest now, there is no need to resolve these mysteries. The vacuum does not demand understanding to function. It supports your existence regardless of whether it is fully known. There is peace in that. The universe does not hinge on our comprehension. It unfolds according to its own quiet rules. Measurement reveals enough for wonder, not enough for mastery. And perhaps that is fitting. The foundation of reality remains partly hidden, not because it is hostile to inquiry, but because it is too subtle to be grasped all at once. The vacuum invites a different kind of knowing, one that is patient, indirect, reflective. As we reach the edge of what can be measured, the questions do not stop. They soften. They become contemplative rather than urgent. And as this chapter settles, one final reflection begins to take shape. If the vacuum can never be fully observed, yet quietly supports everything, what does it mean for us to live within something so fundamental, so active, and yet so profoundly unseen? Part 15. Living inside a sea of quiet energy. What does it mean for us to exist within this restless emptiness? As you rest right now, your body, the air around you, and the space between every atom are immersed in the quantum vacuum. It supports the forces that hold matter together and the laws that allow stars to shine. The calm you feel is not the absence of activity, but the harmony of countless invisible motions beneath awareness. It is easy to imagine yourself as a solid presence in an empty room, separated from the world by the surface of your skin. But physics tells a softer, more continuous story. Your body is mostly space. Atoms are vast compared to their nuclei, and between those atoms stretches a vacuum alive with fields. You're not placed into emptiness, you are woven into it. Every moment of stability you experience depends on this unseen foundation. The electromagnetic force that keeps electrons bound to nuclei arises from fields permeating space. The nuclear forces that hold atomic cores together operate through the same invisible framework. Even gravity, which shapes the motion of planets and galaxies, is a property of space-time itself. The vacuum is not a backdrop, it is the medium through which all structure exists. As you breathe slowly, consider how little separates you from the wider universe. The same quantum vacuum that fills the space between galaxies also fills the space between your thoughts and your breath. There is no sharp boundary, only gradual change in scale. This perspective can feel humbling, but it can also be deeply comforting. You are not isolated in a cold void. You are supported by a universe that is active everywhere, even where it seems most still. The vacuum does not collapse without matter. It remains present, sustaining possibility. Throughout this journey, we have seen how the vacuum shapes reality quietly. It allows particles to exist, forces to act, time to flow, and information to persist. It seeded the universe's structure in its earliest moments and continues to guide its expansion. It even influences the fate of black holes and the direction of time itself. And yet, in daily life, you never feel it directly. This is not because it is weak, but because it is balanced. The vacuum's activity is uniform, steady, and gentle. There is no turbulence, no friction, nothing for your senses to register as disturbance. Calm emerges not from stillness, but from equilibrium. In many ways, the vacuum behaves like a perfectly tuned instrument. Countless vibrations occur at once, but they cancel and harmonize, producing silence rather than noise. The universe hums at frequencies far beyond perception, leaving the surface of experience smooth and quiet. This harmony is what allows complexity to arise without chaos. Atoms form stable structures, molecules assemble, life emerges, consciousness appears. All of this unfolds atop a foundation that never demands attention. When scientists speak of energy filling empty space, they do not mean something violent or overwhelming. They mean something precise. A baseline, a quiet readiness. The vacuum is full, but it is not crowded. This distinction matters. The energy of the vacuum does not behave like fuel waiting to explode. It behaves like tension held in perfect balance. Like the surface of a calm lake, that can carry ripples without breaking. Living inside this sea of quiet energy means that you are constantly supported by conditions you did not have to create and do not have to maintain. The laws that govern atoms and stars operate without effort. They do not tire. They do not fluctuate wildly. They persist. There is a quiet generosity in this. The universe does not require constant intervention to remain stable. It unfolds reliably, guided by deep principles that hold everywhere. Even uncertainty, which might sound unsettling, plays a stabilizing role. Quantum fluctuations do not tear reality apart. They give it flexibility. They allow adaptation. They prevent rigid stagnation. Your own body reflects this balance. Atoms vibrate, but you remain solid. Electrons fluctuate, but chemistry is reliable. Thoughts arise and fade, but identity persists. The micro-level restlessness supports macro-level calm. In this way, the vacuum mirrors the experience of rest itself. When you lie still, your mind does not empty completely. Thoughts drift, sensations flicker, and yet a sense of peace can emerge. Calm is not the absence of motion, it is motion without conflict. The universe seems to have learned this lesson at every scale. There is also something quietly unifying about realizing that you share the same foundation as everything else. The vacuum does not distinguish between star and stone, between body and breath. It fills all space equally. You are as much a part of the universe's structure as the farthest galaxy. This does not diminish individuality. It situates it. Your uniqueness arises not from separation, but from pattern, from how fields and particles are arranged here, now, in this moment. As you rest, nothing special needs to happen for you to belong. Belonging is built in. This understanding can soften the way we think about emptiness. Silence is not lacking. Stillness is not absence. Space is not void. What feels empty is often simply balanced beyond perception. When the night feels quiet, it is not because nothing is happening. It is because everything is happening in harmony. The vacuum also invites a gentle shift in perspective about control. Reality unfolds without intervention. The deepest forces operate continuously, whether or not they are noticed. This does not make human action meaningless. It places it within a larger context of support. You do not have to hold the universe together. It is already held. Even the future unfolds within this quiet framework. Whatever changes come, whatever transformations occur, they will arise from the same vacuum that has always been there, steady beneath variation. There is comfort in knowing that nothingness is not fragile. It does not tear. It does not vanish. It endures, carrying the potential for everything that exists. As this final part settles, the journey comes full circle. We began by asking what happens inside the quantum vacuum. We discovered that it is not empty, not silent, not passive. It is energetic, structured, and essential. And now we arrive at the most intimate realization of all. You are already inside it. You always have been. Every breath, every moment of rest, every quiet thought takes place within a sea of subtle activity that asks nothing of you and supports everything you are. The calm you feel right now is not separate from the universe. It is an expression of it. And as you drift toward rest, you do not move away from reality. You settle more deeply into its quiet foundation, where motion and stillness coexist, and where emptiness gently holds all things.